All right, we're going to go over practice one of the problem one of the practice final. So we want to find the Fourier transform of these three signals. We have an x, a y, and a z. And I've defined a new signal r, where x, y, and z all kind of look like variations of r. So, and we're gonna figure out these Fourier transforms without using the integral over all the time. We're going to use just the tables. From table 4.1, right? So if we have some arbitrary aperiodic signal r of t, and that signal is going to have a Fourier transform, and that Fourier transform we call big R of j omega. And then I have written down two very important properties from that table, and one of them is that the Fourier transform of the time derivative of r of t is equal to j omega times the Fourier transform of just r of t. So this r of t right here is this one. We don't know what r of j omega is, but we know that it is the Fourier transform of r of t. And if we want the Fourier transform of the time derivative of r of t, then it's just j omega times big R of t, or big R of j omega. And then we have the Fourier transform of a time-shifted version of r of t is equal to, well, here we have big R of j omega, so it's equal to that the Fourier transform of r of t times this exponential of e to the negative j omega t naught, where t naught is the shift. Now, uh, notice that there's a minus sign right here. So this t naught, if it's t minus 4, well, t naught is equal to 4. And if it's t plus 4, that's equal to t minus negative 4. Now that t naught is equal to negative 4. Okay. But now let's get into it. So for A, we want the Fourier transform. That's a terrible F. We want the Fourier transform of x of t, which is equal to, that's the Fourier transform of the time derivative of r of t, because of this relationship, what I defined right here, right? Now, if r, God man, if r of t is equal to e to the negative 3t u of t, you can find that on your table. That fits perfectly. That's going to give us a Fourier transform, and this is one that you should have in your head for future classes. It's going to be 1 over j omega times 3, or plus 3, excuse me. So this is the Fourier transform of that. And now we want the Fourier transform of x of t. Well, that's the same as the Fourier transform of the time derivative of r of t. And using this property right here, well, that tells us that it is going to be j omega times big R of j omega, which is equal to j omega times 1 over j omega plus 3. And there's the first one. Now B, we want the Fourier transform of y of t, and that's equal to the Fourier transform of a time-shifted version of r of t, right? And it's being shifted by 2. So there's that. And now using this property right here, well, we know that, well, first let's define t naught. So this right here, t naught is equal to 2. And then we know that the Fourier transform of this, using this time shifting property right here, is going to be e to the negative j omega t naught, which is equal to 2, times big R of j omega, which we know what that is. That is 1 over j omega plus 3. And part C, we want the Fourier transform of z. So let's take a look at z real quick. So z is equal to e to the negative 3 t minus pi over 4 times u of t minus 2. Now, this one's funky because it doesn't match up anything on our table, right? This part, this right here, this time shift and the exponential does not equal this time shift and the unit step. And we can resolve this. We just have to we can't really play with this one. This is telling us when it's on and off. But what we can do is play around right here. We can figure out how to make this look like this. And how do we do that? Well, if we subtract 2 from t and we also add 2 from t, well, then we're not adding anything at all, and we haven't changed the equation. So now we can rewrite this as e to the negative 3 t minus 2 plus 2 minus pi over 4. And I could actually do some double brackets here to kind of make things clear. Let's do this instead. We'll put that there. We'll put this here and that there. And that's times u of t minus 2. And now what I want to do is I want to distribute this 3 throughout. So I'll have e to the negative 3 t minus 2. And then if I distribute this 3 right here, then I would be subtracting. I'll just write it out. So then it'd be minus 3 2 minus pi over 4. And that, why does that look weird to me? I don't know, but it's correct. Or I could rewrite this. I could rewrite this as this, which is probably a little simpler. It'd be e, so we'll have a multiplication sign there, and it's gonna be minus 6 plus, it'd be 3 pi over 4. So all I did there was just distribute that 3 in. And now let's write our unit step there. And when we look at this, well, this is the number. This is the exponential. So 2.71 some change raised to minus 6 plus 3 pi over 4. It's not a pretty number, but it's a number. So we could actually bring that minus 6 plus 3 pi over 4. We'll bring that way out front. And now we have e to the minus 3 t minus 2 times u of t minus 2. And what this essentially means, so let's write that again. We'll have z of t is equal to e to the negative 6 plus 3 pi over 4 times, and if we take a good look at this, let's look at this and compare that to what y is, which y of t is right here. When we look at that, we see that they are exactly the same. So we could actually just write this coefficient right here and then write y of t. So the Fourier transform of z of t is equal to the Fourier transform of e to the negative 6 plus 3 pi over 4 times y of t. Fourier transform is a linear operation. Right here is we have a coefficient, so we pull that out front. E to the negative 6 plus 3 pi over 4 times the Fourier transform of y of t, which we already figured out y of t. So the Fourier transform big Z of j omega is equal to e to the negative 6 plus 3 pi over 4 times e to the negative j omega times 2, all that multiplied by 1 over j omega plus 3. And there are your Fourier transforms of a or x, y, and z here. Thanks.